Why can you see straight through a pane of glass but not through a piece of wood, or a slab of metal, or your own hand? Let's set the rules first. Same sunlight, same thickness, just different materials standing in its way. One lets almost all of that light pass straight through. The others stop it cold. Something invisible is happening at a scale smaller than anything you've ever seen with your eyes, and it decides whether a material is a window or a wall. Here's what's actually going on inside that glass. Start with light itself. Light isn't just brightness, it's energy, moving in tiny packets called photons, and every single photon carries a very specific amount of that energy. Max Planck figured this out in 1900, and Albert Einstein confirmed it in 1905 when he explained the photoelectric effect. Light doesn't arrive as a smooth wave of energy. It arrives in discrete little bundles, like coins instead of a stream of water. Now think about atoms. Every material on Earth is built from atoms, and every atom has electrons orbiting it in specific energy levels. Picture rungs on a ladder. An electron can sit on one rung or another rung, but never in between. To jump from a lower rung to a higher one, that electron needs an exact amount of energy. Not close, exact. So what happens when a photon of light hits an atom? If the photon's energy matches the gap between two rungs, the electron absorbs it and jumps up. The photon disappears. Its energy gets converted into heat or gets re-emitted in a random direction. Either way, that beam of light doesn't make it through. But if the photon's energy doesn't match any gap on the ladder, something remarkable happens instead. The electron simply can't absorb it. The photon has nowhere to go, so it keeps moving, straight through the material, as if the atoms weren't even there. This is the whole secret. Transparency isn't about a material being empty or thin. It's about a mismatch, a missing rung on the ladder, right where visible light needs one. Let's put real numbers on this. Visible light photons carry between about 1.8 and 3.1 electron volts of energy, depending on the color. Red light sits at the low end. Violet sits at the high end. That's the entire visible spectrum, the whole rainbow you can see. Now look at ordinary glass, which is mostly silicon dioxide, the same compound found in sand. Researchers studying the electronic structure of silica glass have measured its band gap, the energy jump an electron would need to absorb a photon, at roughly 9 electron volts. That's the work behind decades of solid-state physics research, formalized in detail by physicist Charles Kittle in his widely used textbook on solid-state physics, still a foundational reference for materials scientists today. 9 electron volts. Visible light tops out around 3. Do you see the gap? Every single photon of visible light hits that glass and simply doesn't carry enough energy to knock an electron up to the next level. There's no rung to land on. So the photons pass straight through, one after another, completely unabsorbed. That's why you can read a book through a window, why an aquarium lets you watch fish swim, why a car windshield doesn't block your view of the road. Now compare that to wood, or your hand, or a slab of steel. Metals are a different story entirely. Metals have electrons that aren't tied to specific rungs at all. They flow freely like a sea, which is exactly why metals conduct electricity so well. But that same freedom means there's always some available energy level for a photon to be absorbed into. Metals absorb visible light almost instantly, at the surface, which is also why polished metal looks shiny instead of see-through. The light gets absorbed and then re-emitted right back out. Wood and skin are more complex. They're packed with countless different molecules, each with its own ladder of energy gaps, layered on top of each other, scattering light in every direction before it can travel more than a fraction of a millimeter. Even if some of those gaps don't match visible light, so many other materials are in the way that light bounces, scatters, and gets absorbed long before it ever reaches the other side. So transparency requires two things working together: a band gap wide enough that visible light can't be absorbed, and a structure clean enough that light doesn't scatter into a million directions before it escapes. Glass happens to be extraordinarily good at both. But here's a twist. If pure silica glass is so good at letting every visible photon through, why does stained glass come in blazing reds, blues, and golds? Why isn't every piece of glass on Earth perfectly clear? The answer is that glassmakers cheat the system on purpose. Add a pinch of cobalt oxide to molten glass, and you introduce new atoms with their own, different energy ladders. Cobalt creates gaps that do match the energy of red and green light, so those colors get absorbed. Only blue light survives the trip through, which is why cobalt glass looks a deep, saturated blue. Add gold chloride in tiny amounts, a technique traced back to Roman glassmakers as early as the 4th century, and you get the famous ruby red glass, still studied by archaeologists today, caused by microscopic gold particles absorbing green light and scattering red. Every stained glass window is really a controlled experiment in exactly the physics you just learned, just run in reverse. Instead of avoiding energy gaps that match visible light, the glassmaker deliberately builds them in, so transparency and color aren't opposites. They're the same rule, pointed in different directions. Now scale the question back up to the everyday world. Here's where it gets more interesting. Glass isn't a crystal. Its atoms aren't arranged in a neat, repeating lattice like a diamond or a grain of salt. Glass is what scientists call an amorphous solid, atoms frozen in a disordered, liquid-like arrangement because the molten material cooled too fast to organize itself. You'd expect that disorder to scatter light everywhere, but it doesn't, and here's why. The disorder in glass happens at a scale far smaller than the wavelength of visible light. Visible light wavelengths run from about 380 to 700 nanometers. The atomic scale irregularities in glass are far tinier than that, so the light essentially can't see them as obstacles. It's like trying to trip over pebbles that are 1,000 times smaller than your foot. They simply don't register as something to stumble over. This is a detail confirmed repeatedly through materials science research at institutions studying optical glass, including work published through Corning, the company behind decades of specialty glass innovation, used in everything from telescopes to smartphone screens. Their research has shown that eliminating larger-scale defects, bubbles, and impurities is what pushes glass transparency close to its theoretical physical limit. So the real question was never just about atoms and energy gaps, it's also about purity. Ancient glassmakers didn't understand any of this, not the band gaps, not the photons, but they discovered through trial and error, going back over 3,000 years to early Mesopotamian and Egyptian craftsmen, that the fewer impurities in their sand and ash mixture, the clearer the glass became. Every bubble, every fleck of iron, every stray mineral created a new scattering point, a new obstacle for light to bounce off of before reaching your eyes. Modern optical fiberglass, refined for telecommunications, achieves purity levels so extreme that light can travel for over 60 miles through it, before losing half its intensity, a benchmark studied extensively in fiber-optic research pioneered by physicist Charles Kao, whose work on light transmission through glass fibers earned him the Nobel Prize in Physics in 2009. Read that again, 60 miles, through solid material, and the light barely dims. That's not empty space, that's glass, engineered so precisely that almost nothing gets in light's way. And it's worth asking what this same rule does elsewhere. Diamond has an even wider band gap than glass, around 5.5 electron volts of separation for its highly ordered crystal structure, which is part of why a well-cut diamond looks so brilliantly clear and lets light bend and sparkle inside it, rather than being absorbed. Water is transparent for a similar reason, its own molecular energy gap sitting safely above what visible light can trigger, which is exactly why sunlight can reach dozens of meters down into open ocean water before it finally fades to darkness. Ice, quartz, sapphire, even the clear plastic in your phone screen protector, every one of them is transparent for the same underlying reason. A mismatch between the light hitting it and the energy an electron inside it is willing to accept. Now bring it back to something you can feel. Every time you look through a window, you're relying on a mismatch between the energy in sunlight and the energy gaps inside billions of silicon and oxygen atoms locked together in a disordered, glassy structure. You're relying on purity refined over 3,000 years of human trial and error, and on quantum rules discovered barely a century ago. None of it is obvious. None of it is guaranteed. Change the atoms, change the gap, and that same window becomes a wall. So why is glass transparent? It's not because it's empty, and it's not because light passes through nothing. It's because, deep inside every atom in that pane, there's a gap too wide for visible light to bridge. A missing rung on a ladder that lets your entire world stay in view.